I'm Barth from Facebook, and I'm going to be talking about how we use profilers at Facebook, specifically profilers in production, to get the most out of our efficiency efforts. So first, a little bit about me. So I started at Facebook after school a little over a year ago now, and I joined a team that's focused on efficiency in our data warehouse in the compute engines, so Spark and Presto. But most of my work has been specifically for stuff on Spark, and of my work there, it's almost all been on profiling tools. So that's my area of expertise here. I do want to kind of preface this discussion by talking about why we even want to spend all this time investing in tooling just for efficiency. So obviously, we have a very large Spark distribution. We've got a lot of machines, and when there's a lot of hardware involved, any little efficiency improvements you can make are going to go a very, very long way. And because of that, it's very worth it for us to kind of lay the groundwork for our efficiency. And profiling tools kind of do a great job laying that foundation and helping us figure out what's going to get us the most bang for our buck in terms of efficiency work. And it's because of that we found that it's worth it to spend all this time investing in tooling, even though it's not immediately giving us returns in terms of efficiency. It's great for the long term, and all this time, even in the future, when things are pretty optimized, any little bit of efficiency we can squeeze out with that is still going to go a long way. And largely as a result of our efficiency works and our profiling tools helping to guide that, we've gotten 2x throughput on our Spark workloads through the past 18 months, like measured in our actual production. So the way I kind of want to frame this and talk about why we use profiling tools, how they help with our efficiency, is through a few questions, like what do we look at when we're measuring performance? So the first one, obviously a very complex topic, can't really be distilled into this, but this is just kind of how I want to frame it. So the first question you might ask is, and probably the most obvious, what can we actually improve? And that's the obvious use case for profilers, just figuring out where in the code is spending the most amount of time and what we can do to potentially improve that. And this manifests itself in two main ways. So the first one, in terms of like micro optimizations, what sorts of things can we, which parts of the code might be doing things inefficiently, where we can go in and make immediate improvements. And that's something that profilers can really show us that we might have no idea about otherwise, where we look at the profile and we see maybe some method is responsible for 2% of CPU time, and we don't expect that at all. Maybe we wouldn't expect a whole lot of time in that method, and we can go in and make some sort of change, or take a closer look, and the profiler really helps us figure that sort of thing out. But then there's kind of the larger macro projects where we may have already had some idea of some projects we might be able to take on in terms of efficiency, but we don't really know exactly how much in terms of our production workload. Like, if we make some improvement to this code path, will we see a 5% or a 10% win? And that can sort of, profilers can help us frame this discussion and prioritize certain things over other things. So it gives us this improvement in two different ways, where we can figure out inefficient parts of the code, but we can also prioritize our ongoing efforts. Now the second question I want to talk about here is actually validating our improvements. So obviously, we're not going to just put things straight into production and then validate them that way. There's going to be a lot of different things we go, like unit tests and then micro benchmarks to make sure that things are actually getting more efficient. But we don't really know exactly what's happening until we actually look in production, because all of these environments, like micro benchmarks and looking at some past queries and stuff, we may be trying to simulate production as well as possible in the easiest way possible, but we're not actually going to know what's going to happen until we put it in production. There's always going to be some sort of unintended consequences of changes we make, and profiles really make that obvious. So, we might be able to just naively look at CPU time of before and after we make a change and say, okay, we see a 0.5% or a 1% improvement. Now, there's going to be a lot of variance in big systems like Spark, so can we really trust that with one measurement? And what if our change actually should be a 3% win, and then we see 1% because something else regressed by 2%? Profiles make this extremely obvious because we can zoom into the exact things we want to look at. So if we are trying to optimize some method that from 2% to 1%, and we see a 1% overall CPU win, that could be variance. But if we look at the profiles, we can actually see the profile beforehand. We're seeing 2% time spent in that method. We look in production afterwards. We see it actually went down to 1%. Everything's great. And then, like I kind of alluded to earlier, there's also the side effect of something might jump out, like, oh, this other method went up from 3% to 4%. Why would that be? And the profile, it really allows us to zoom into these particular pieces of code that are relevant and validate things a lot better. And I do want to call out this sub-bullet here with parameter tuning. And by this I mean maybe we want to change some JVM parameters like inlining behaviors, or maybe we want to change some stuff in Spark like configuration. These are the sorts of things where obviously if there was something that was just optimal for all workloads, that would be the default and no one would ever care about it. And the reason we can tune it is because it's, increasing a value might help in one way and hurt in another way. And this is the sort of thing where looking at a profile can give you a lot more context around how this tuning is actually affecting things, and maybe we expect to see certain things change based on profiling, and it can give us context on not only how things change when we tweak these settings, but also how that might affect any future changes we're making in terms of efficiency. And the last question I want to talk about here, which I think can absolutely not be understated, is catching regressions. Because when we're making changes and users are creating new queries and we're changing things in the engine, there's always going to be stuff that gets worse over time. That's the reality of this sort of thing. Is the default behavior without any maintenance is things are going to get worse. And so catching regressions is a huge part of any good efficiency work. So how do we go about catching regressions? Profilers are great for that because we spend a lot of time looking at the breakdown of methods, which methods might we be able to optimize, and we're spending all this time trying to identify areas for our efficiency work. And then a side effect of that is we become very familiar with what our production code looks like, what code paths it commonly goes down. And so when something changes, we notice that immediately. So if there's some regression, whether that's some job misbehaving or some actual change we made to the engine that had some unintended consequence, something along those lines, we're going to notice that very quickly. And these sorts of things we found can really slip through the cracks. Like when we first started building our muscle around profiling tooling, there were some really obvious low-hanging fruit that immediately jumped out that were just completely overlooked. And without the profiling, there's no obvious way of catching that. But it's the kind of thing that could just be a 1-hour fix and yields great results. So I've kind of built the case for profiling, but how is performance usually assessed? You've probably heard a lot of people in talks here talking about the TPC benchmark, specifically TPCDS for Spark SQL for data warehouse type workloads. And there's a lot of value in these sorts of things. If you're not familiar, the TPC benchmarks are just these general benchmarks that try and capture all of the aspects of the compute engine. So everything that's important to good compute engine performance is going to be captured in these benchmarks. And it's a way of not only comparing before and after, but comparing different compute engines against each other. And this sort of thing is extremely valuable. especially for an open source project like Spark, where people are going to want to communicate any efficiency improvements they make to other people. And if they just have some benchmark, or if they're talking about their production workloads, people aren't going to actually know what that means for them. So having these sorts of queries where everyone knows the TPCDS benchmarks, and if someone says, oh, we've improved TPCDS by 10%, everyone in the community knows what that means. They can dig into these queries, the particular queries in TPCDS, and really understand what's going on in the changes. And it also has the benefit of being able to track before and after over long periods of time. So we can look back and say, we've done all of these efficiency projects over the past 12 months. How much have we actually helped things? And we can look before and after. It's the exact same queries, so we can say, on this benchmark, we have improved the engine by this much over this amount of time. And that's something that we can't quite get just from looking at production profiles. But there are some cons to benchmarks like this. And that's that not all workloads are created equal. So what I mean by that is, in our production workloads, there's going to be some things that might be overrepresented in TPCDS or underrepresented, where maybe TPCDS cares a lot about these certain features, but we don't actually use them in production. There's a lot of differences specifically at Facebook that I want to highlight to kind of make this point. So in Facebook, we have less joins and aggregation compared to TPCDS. So if we were to invest some efficiency efforts there, and we say, oh, we've done some prototyping here and got some basic functionality, and it looks like we're going to see a 15% improvement in TPCDS. Great. And we go, we execute, we make the change, and then we look in production after the fact, and oh, actually, it was only a 5% improvement. Obviously, it's still something that's good to take on, but it could kind of mislead us in terms of what to prioritize. And in cases where it might not be a strict improvement, where there's actually a trade-off, maybe TPCDS tells us that something would be good, and it's actually going to hurt for us. And then there's some things that are going to be completely missed. So stuff like UDFs, user-defined functions. There's countless user-defined functions at Facebook, and these are not going to be represented at all. And that's a huge part of our efficiency work, because if a lot of our CPU time is going into UDFs, then work around optimizing individual UDFs, as well as optimizing, in general, how UDFs are handled in the engine, those are things that are going to be very important, but we're not going to be able to measure them at all in TPCDS. And transforms as well, another thing in the same vein there. By transforms, I mean that's when we have a query calling into some like Python or C++ code, and they're used pretty extensively at Facebook, and they're going to be completely missed. And then complex data types. Our workloads are heavily skewed towards complex data types, so maps, lists, structs, and these are the sorts of things where projects in that space are going to be extremely useful for us. And if we're just looking at TPCDS, we might not understand what value we're actually going to be adding. And then, so you might be thinking, well, why don't you just make a benchmark that's more representative of your workload? And that's something we have invested somewhat in, because, like I mentioned, it is very good to have something that allows you to track performance over time. You can just run the same benchmark when you make an improvement and look at any sort of CPU time difference. But the fact is, workloads evolve, and sometimes very quickly. And so if our workload's changing a bunch over time, we're constantly going to be playing catch up with trying to make our benchmark represent it as well as possible. When we make some new changes, we're going to have to add that feature to the benchmark. And then if we're changing the benchmark all the time, then suddenly we lose that benefit of being able to compare before and after in the first place, which is a lot of the value that we're getting from it. And so that's why profiling in production, it allows us to not worry about evolving workloads. They're automatically going to be captured because we're taking the data directly from production. If something changes, we see that change, and we can kind of adapt as that happens. So I've been talking a lot about production profiles. How exactly do we do it? So some basic architecture here. So in the top left, you see we have our Spark machines, and on every machine, we have a profiler running. So we do sample, but it's not on the machine level. We sample in terms of time. So because we want to capture what's happening on every machine. We can't actually have them continuously running on every machine because not only would that be just too much data, it would also add some overhead. The profilers we use are they're not very high overhead, but even a couple percent, like I mentioned, makes a very big difference at such a large scale. So we can afford to sample pretty heavily with the scale we're at. So each profiler is profiling for some percentage of the time on the host. And we tag metadata along with the stack frame. So the profiler itself is just returning stack frames, or stack traces, sorry. So it's just sampling stack traces from the machine. And then along with that, we kind of capture some other information. So stuff like which cluster did we get this stack trace from? Or what did we run on the command line, which version of Java, stuff like that. But also extremely importantly, one thing we've done is we have our jobs run with a job name and a job ID as part of the environment. And we can parse that when we get these stack traces. And so along with every stack trace, we also have the job that it corresponds with. So we have this logging service, our unified logging service that we log all this data to. Scuba, you might know about it. And I think similar would be Apache's Pinot for like an open source version. So we aggregate this all in Scuba. And thanks to tagging this metadata, we're able to not only look at profiles for all of our production as a whole, but we're able to zoom into these particular characteristics. So we can say, let's look at on this particular cluster, or more importantly, let's look at the profile just for this particular job. And so small jobs we might not have enough samples for because we are sampling pretty heavily, but for large jobs, which is what we really care about optimizing, we can take the profiles just from that job thanks to the metadata that we've gathered along with the stack traces. So like I mentioned, and on the Spark team, we usually look at these kind of as aggregate queries in the bottom right. So we'll have a breakdown of here's the CPU time percentage in all of these different methods. And there's all sorts of different ways we can look at this data. I'll get more into that in a little bit, the different ways we look at the data. But so that's how we usually look at it in the Spark team. We look at these different aspects of what's actually happening in the engine. But users are somewhat interested in these profiles as well. They just can't dive into the meat of the Spark engine. Like our users who are writing the queries, they're not going to understand the execution of Spark to the point that they can look at the methods and say, oh yeah, I know what my job is doing because of this profile of Spark. It's just far too heavy. So we run this pipeline which classifies these into high-level frames. So we'll check and say, oh, if we see this particular method, then we know this belongs to the read code path. So we'll just count this as read or write, or this is part of a transform, or this is part of shuffle, stuff like that, or part of a UDF. And then we surface this information to users, as you can see here in the bottom left. And this gives a lot more actionable information to users. Rather than having to look at some heavyweight profile, they can just say, oh, look at this. 88% of the time spent in my job is just writing. So if they're looking to optimize their job, they don't need to worry about cutting out reading or if anything weird is happening. They know all the time's going into writing, so if they can write less data, then they're going to see pretty much a perfect correlation with the actual time spent in their job. And this is extremely important because our efficiency efforts can only go so far in the actual engine if all the queries are extremely inefficient. You know, we can try and do stuff in the engine to make up for queries that might be doing something that's ill-advised, but sometimes users are going to be reading or writing data that they don't really need, and maybe they don't even realize how much that's contributing to slowness in their pipeline, and nothing we do in the engine is actually going to help with that. So our efficiency effort wouldn't be complete without having some way of helping people optimize their pipelines. And this profiler information, thanks to us being able to classify into high-level frames, has kind of given us another angle of attack in our efficiency work. So that's the general idea of how our profiling is set up. But how do we actually do the profiling? So we actually use two different profilers. for Spark. We have an internal profiler, which is, it's kind of just a general profiler for Facebook. It's used across Facebook, not just in Spark, not just in our data warehouse, not just in Java. It's all across Facebook, which means it's capturing everything that's going on in the engine. So all the processes, any transform that we're calling into is being caught by this profiler, but it's not very good at dealing with some of the weirdness in the JVM. The JVM, there are ways of generally profiling the JVM and getting some meaningful data without a Java-specific profiler, but there's some gaps there. For instance, some of the high-level frames, it can't read interpreter code, so a lot of the high-level frames are just marked as interpreter. And when we're trying to look at the macro code paths, that's not very useful to us. And in general, it kind of isn't as smart about attributing some things to make up for what's going on in the JVM. So we also use async profiler. It's not developed at Facebook. It's a third-party open source solution. And it's a Java-specific profiler. It knows a lot about what's going on in the JVM, and it doesn't suffer from some of the issues that other Java profilers suffer from, like safe point bias. I don't really have time to go too much into that, but in the GitHub page that I've linked here, there's a lot of information about async profiler. So if you're curious about that, you can go read about it there. The reason that this isn't the only thing we use is because it's only running on our Java processes. So it's missing some context about stuff like transforms. And that's especially crucial because of like the user-facing profiles I talked about. If we're, users want to know if there's time being spent in transforms. So if we're only looking at the actual Java code, we're going to be missing a big part of the picture. And even for our understanding, it's very good to have information about transforms. And yeah, one other thing here, async profiler has a heap allocations profiling mode, which isn't without its problems. It can only profile allocations and doesn't know anything about the actual lifespan of objects, but there's still some useful insight that can be derived there. And like I mentioned, we take these profiles and then we aggregate them in Scuba, our unified logging service, which allows us to very quickly query and look at the data, slice and dice it in a lot of different ways. So now let's talk about how we actually view this data. So the first one, this is kind of our general bread and butter where we'd go to try and find some areas to optimize. We call it the graph profiler internally. And it just shows a list of the top methods in terms of exclusive and inclusive time. So what that means is exclusive is time that's actually spent in the execution of that particular method, not to any of the methods it calls into. Just like if the method's looping and doing a bunch of computation, it's going to be time spent in there. Inclusive time includes everything that that method calls into. So basically, exclusive is any time that the method is at the top of the call stack, and inclusive is any time the method appears anywhere in the call stack. And so this is very nice, and both inclusive and exclusive are useful in different ways. So exclusive is good for the micro-optimizations I talked about, where there's just something inefficient happening in some method, maybe some blind spot we had or something we overlooked. And so when we're trying to look for potential micro-optimization opportunities, we would generally look at the exclusive time and look at things that might look out of place there. The inclusive time is much better in terms of getting a macro-level view of the code and exactly what's happening. So let's say we're interested in how much time in general throughout all of our production workloads do we spend in reads. So we could just search here for the read method and then see the inclusive time spent there. I'm not sure if there's a good open source thing to display information in this way, but this can be achieved with ad hoc queries like exclusive time. You would just check the top of the call stack for that method, and inclusive would be anywhere in the stack. So this is the sort of information that you can get just by running manual queries. This UI just gives us a much easier way of looking at the data. And so we could even zoom in. If I were to click on one particular method here, we could get we could dive even deeper here, look at the parents and children. So parents is saying what % of samples did we see that this method was called into by some other method. So like what % of the CPU time of this method did it come from some other method, and then children is what percent of the time it calls into other methods. And then we could click on these to kind of go up and down the stack, just kind of traverse the code, or the code paths, and understand what's going on. And here leaf means time spent in the execution of that method. So leaf will correspond to the exclusive time. Then there's the Icicle chart. You might know it as the flame graph. It is blurred out, so you don't need to get your eyes checked. So the Icicle chart, if you're familiar with the flame graph, it's the same thing. The Icicle chart is just the root, and then it grows. The root's at the top and grows down. The flame graph, the root's at the bottom and grows up. But flame graph is an open source sort of thing, and actually Async Profiler natively or like automatically produces flame graphs out of the box. So this is the sort of thing, just by running Async Profiler, you can get this kind of view. And this is another very good way of visualizing the code at a macro level. So we can see exactly how much percent of time is spent in these different methods, and visually see like what percent of the time it's calling into other methods, and just get a great macro level view. We could click on any one of these and zoom in to refocus with that method as the new root. So the fact that the words aren't, or the names of the methods aren't showing up in some of these deeper code paths, we could zoom into that. And so this makes it really easy to jump around to different parts of the code path and see what's going on. And it's great for identifying anything that might look out of place at a high level rather than at a micro-optimization, particular methods execution level. Now, one more view here. The table, it's basically just a group by. Just a visual way of doing a group by. It makes it very easy for us to do this sort of thing. And you can see here I'm grouping by app ID. So that's where I mentioned earlier we tag metadata to understand, to get job level information. So this here, since we're grouping by app ID and then we're ordering by the number of samples we have for the app ID, it's just telling us which jobs spend the most time. And we can get that information from other places, but this is very useful if we add other filters. So we could group by app ID, but we could also filter on the stack containing some particular method. And then we could see which job is spending the most time in a particular method. And we can get all sorts of advanced breakdowns with this. And this is another thing that the UI is nice for us here, but this could really be achieved easily with a manual query, just grouping by this thing where some filters you're interested in. And the last one I want to talk about is the time series. So this is a great way of kind of seeing when some sort of regression might have happened. It's not going to be exact, but so in this particular case, you can see I'm filtering on the stack containing some particular UDF. So this is the percent of time that's spent in this particular UDF or any execution that it calls into. And in this case, this was a known thing. We made some optimization to it, which then caused it to be named differently. So you can see the samples go to 0, but then we had to revert it because of an unexpected bug, and then you can see the samples go back up. And in this case, we knew exactly when we did this, so it's not super insightful to see. But if this was some regression that, say we had a regression a month ago, and we only noticed it just now, and so we didn't actually know which release it might have been a part of, if we look at this time series graph, we can say, okay, we see there was a huge spike at this one particular day. Let's figure out which release happened that day, and it might give us some more information as to how things have shifted over time. And even if it's not a regression on our side, if we see some jobs, some big jobs started doing something new, we could take a look at how the usage has shifted over time, and it could give us a lot of insight into some of our efficiency work where we might see some trend. And we see that some method is getting called a lot more often, so it's worth spending more time looking into ways to optimize it. So what I want to kind of leave you with here is we have all this profile data, and I've showed you a bunch of different ways of looking at it, and they're all very useful on their own. There's a lot of information here. But where the real power is all of these different views are different ways of slicing and dicing the data, and they work very well together because they display the data in different ways. So we can kind of jump back and forth in between these different views to get an understanding, a much deeper understanding of what's going on than we could in any particular one. So let's say we're looking at the graph profiler view, the first one I showed, and we spot some regression. We're just browsing through the graph profiler view, trying to get some ideas for micro-optimizations, and we see that something jumped up. And we want to know what happened. So what I've found over time from working on these sorts of things, and my first instinct is, let's group by jobs. So we'll take that method, we'll filter on the job, and we'll group by jobs, and get a list of which jobs are most responsible for calling this method. And we've had times where it's one job misbehaving, and like 99% of the time spent in that method is just one job. And so there's some regression. We've gone from spotting it to root causing it to a particular job within 2 minutes. But obviously, sometimes we're not so lucky. Maybe it's some inefficiency we introduced on our side in the engine, and we have to look at the, and we have to look at the time series graph and help figure out at what point this was introduced. And then we could dive deeper, like in the graph profiler where I showed you can click on it and go up and down the stack. There's a lot of different ways we might have to look at the data. It's not always going to be as easy as what I just described, but I just kind of wanted to make the point that there's a lot of different ways of looking at the data, and I've kind of come up with new ideas for this all the time when investigating things, and I still feel there's a lot of untapped potential with a lot of these different ways of looking at the data, but the bottom line is we have gotten so much mileage out of our profiling tools in terms of our efficiency work, and it's been absolutely worth it for us to spend the time to build up our muscle in this area. And so to anyone who's seriously planning to invest a lot of time into working on efficiency, I absolutely suggest that you spend your due diligence investing in tooling so that you can look at information in ways like this. So, thank you.
Thanks, Adam. We have time for a few questions.
So I'm glad that I didn't go home and came finally to this talk, because it's a really great talk. Thank you. And regarding the flame graphs, and not just flame graphs, regarding the profiling overall, are you profiling not only a driver, it seems, but you're profiling executors as well, right?
Yeah, the executors.
And as far as I remember, I think Profiler needs an OpenJDK to be installed and to run so you have to run the Spark on OpenJDK, right?
Sorry?
You have to run the Spark distribution on the OpenJDK JVM to use the sync profiler, right?
Oh, I'm not actually 100% sure, but.
No? Yeah, that's great, okay. And if you are profiling the executors, I did some kind of this stuff in our company, but there are lots of frames from this code generator of Spark. I'm trying to remember how it's called, but still, okay. And how can you find the UDF, as you said, like the one UDF that was generated and processed and took so much time?
Yeah, so that is one thing that the generated code is a lot harder. Like in the profile, it does kind of just show up as generated code. When I was talking about UDFs, we have a lot of like legacy like Hive UDFs, and those are handled differently and not code gen. So yeah, anything that's being code gen is a lot harder to kind of look at with profiling. Yeah.
Any other questions?
So you showed us that you used a sync profiler for Java profiler.
Yeah.
But what I don't understand clearly is the other part of profiling, how it's done, if there is an open library to understand the
So the other profiler we used is like, it's an internal profiler.
Okay. So you.
It's a pretty general profiler, just like, but yeah, it's not an open source.
You just analyze the fiscal plan from Spark, or is based on other things?
Sorry, one more time.
Those information about transformation you extract from the fiscal plan, or
No, the profiler, it's profiling like everything that's going on in the machine. So when a new process is started for the transforms, it's caught by our internal profiler. It's just kind of set up to profile what's going on
okay, thank you.
on the machine. Yeah.
Thanks for the talk. Sorry. So I'm also a younger developer, and one of my challenges when I do profiling is always interpreting the results. So if we don't always have, I notice you guys use a lot of like proprietary tools to interpret the results of your profiling. Are there just any good resources or things that you picked up in general as a way of like, approaches to understand the profiling better?
Yeah, this is something where a lot of it's kind of been experience. In terms of visualization, I know that like the UI elements we have that are proprietary like do go a long way in helping that, but I think a lot of it can be interpreted just by manual queries, but it is very difficult to kind of look at the data in the way that's going to be the most useful. And a lot of what's been good for me is like I'm digging into some regression that I found, and I'm just kind of stumped for a while, and I don't know what's going on. And then I come up with some idea, and that immediately leads me to root cause, and then that's something that's kind of in my arsenal for the future. So I think a lot of it just comes from experience and using them to solve problems in the past, and it gets a lot easier as you go into the future, yeah.
Okay, thanks.
You guys are making me work.
And finally, regarding the trade-off of using the async profiler on the executor side, did you measure how much time or maybe in percent how it degrade the performance of the whole executor? So
we sample pretty heavily. Like we have it running with a certain probability like every minute. So it's sampled heavily enough that it's negligible.
So it's like run one a minute for some time?
We've built like a wrapper around it that we use to deploy it internally, where we have the wrapper that just wakes up and then it calls async profiler to run for a couple seconds every now and then.
Okay, that's great.